Cleavage and fracture are probably the two most difficult mineral properties to grasp when you first start studying minerals. So I want to show you a few examples of different minerals and different examples of cleavage and fracture to help you see what to look for in your own mineral samples. Now, as you'll see, the samples that I have are not from our rock and mineral kit, and one of the reasons for this is because our samples in the rock and mineral kit, they're really small, and it's difficult to see cleavage and fracture in really small samples. So I want to show you some examples of a little bit larger in size so we can see the cleavage planes in the minerals that have cleavage and just what fracture looks like in a mineral that has fracture instead of cleavage. Now, one of the first things to remember when we are determining whether a mineral has cleavage or fracture is that cleavage will always be smooth sides to a mineral that have been formed due to the breakage of that mineral. Now, the reason why I want to start with that is because there are some minerals that haven't been broken yet. And if they haven't been broken, then you will instead be looking at a crystal shape. Now, let's start with this sample of quartz. Quartz, as we have already studied, does not have cleavage. It has fracture. And so when we see this sample of quartz, we see these long, smooth sides, we see these points at the end, we have multiple crystals in this particular sample. This is how that mineral grew. It has not been broken. And so that's why we see those smooth surfaces in this sample. Now, if we flip it over, we'll see the fracture. We'll see where this sample was broken off of in order to be its own sample. Now, if we look closely at a sample of quartz, we are bound to find conchoidal fracture. And because this particular sample is transparent, I actually see some small pieces of portions within this crystal that display conchoidal fracture, and that means it has experienced some force on the inside of that crystal in order to form that conchoidal fracture. But I've got a great example here of just a piece of gravel that I found out in my driveway that displays the conchoidal fracture. Now, this is more than likely a piece of yellow chalcedony. And if we take a close look at this sample, we'll actually be able to see that conchoidal fracture. And that conchoidal fracture occurred when this sample broke. So I might have driven over it with my car or my lawnmower, and it might have broken. And so we see those rings, those rounded rings, where this mineral has broken. And that's a great example of conchoidal fracture. So conchoidal fracture, and now chalcedony, I didn't mention this, but chalcedony is a variety of quartz, and so it displays all of the properties that quartz would display because it is made of the same thing. And we see that conchoidal fracture right there. Now, to get into cleavage, now cleavage is when you look for those smooth surfaces. So let's start with the simplest type of cleavage. I'm going to grab this stack. This is just a bunch of muscovite and biotite. Okay, these are just a bunch of old lab samples that I have. Now, the reason why, you know it, you have it in your rock and mineral kit. This stuff is thin. Muscovite, if you peel it off thin enough, it can be transparent. So we are dealing with these really thin sheets of this mineral, and it's really cool because there are not many minerals that do this, but you can peel off these, just these paper thin layers of muscovite. And the reason why you're able to peel muscovite, I know you can do this with biotite, but I would not recommend it unless you're willing to lose a fingernail, because biotite actually is bonded together a little bit more tightly than muscovite, and it's a little bit more difficult to peel off, even though I just did it right there. But this muscovite and the biotite, you can peel it off into layers because this mineral has cleavage in one direction. So that means there are weak bonds situated between each of the layers in this mineral. And those weak bonds will break first when you're trying to break this mineral. And that's why you can peel it off like pages in a book. So that's cleavage in one direction. Let's look at cleavage in two directions. So this is a piece of potassium feldspar. Now, potassium feldspar, if I were to take a rock hammer and break this sample, it would create smaller pieces that have smooth sides on just two sides. So we will have a smooth side being created, and when those smooth sides come together, they form about a 90-degree angle. And so you see the angle that's being made with my pointer fingers? We see that 90-degree angle. And that's what we mean by cleavage in two directions. Cleavage that creates a 90-degree angle with the sides as they intersect. Now let's bump up the level here. Now let's see here. We've got samples of calcite right here. Here's some clear samples of calcite. Now as we move around this sample in the light, ooh, there we go. We can see the cleavage planes. You see those smooth surfaces. Now remember, cleavage, it only happens when you break a mineral. So we need to look for broken surfaces. And these broken surfaces here show us the cleavage. Now, calcite has cleavage in three directions that do not meet at 90 degrees. And so as we look at these sides here, you can kind of make that out. Oh, there we go. So we got cleavage at three directions that do not meet at 90 degrees. That's why we have this general rhombohedron shape to calcite, is because those angles are not at 90 degrees. They're a little bit off of the 90-degree angle. And so you get these little rhombohedrons. Now that is different from halite. Now this, okay, I brought my salt shaker in here. Of course, it's a little bulldog full of salt. If you take some salt out of your salt shaker and magnify it, it's going to look like this. So here we have cleavage in three directions, but those cleavage planes meet at 90 degrees. And so when we have three directions of cleavage and they all meet at 90 degrees, we get cubes. And so that's why the salt crystals in your salt shaker, if you were to pour some out and stick them under your magnifying glass, they would look like little cubes. And even in just the bigger size of this, you can see that we've got a cube for our halite. Now, not all sides of halite show a cubic structure, and so if you break that halite in just the right way, you will get one of those angles not producing those cleavage planes. So instead, you would get fracture. And we saw that in the sample of the potassium feldspar. Since we only have two directions of cleavage, the other directions will display fracture, so that irregularness of the broken side. That would be our fracture. All right, so that's our breakdown of cleavage and fracture. Now, this one is a little bit more of a more difficult property to comprehend at first. And so if you have any questions about it, just let me know.